Hey y'all, today we're going to be talking about logarithms and how to derive them. To start off, we'll discuss what logarithms actually help describe, and then we'll get into their derivatives, particularly the natural log, or log base e. So without further ado, let's dive in. So let's go ahead and motivate where these logarithms actually come from. And they're actually going to come from solving exponential equations. So, for instance, a natural question we could ask, what power x solves the equation 2 to the x equals 8? Well, one thing we could notice is that 8 is just 2 cubed. So, x better be 3. And that would be a perfectly good answer and the correct answer. However, this was highly dependent on 8 being such a nice number, meaning so closely related to powers of 2. What if we ask a different question? For instance, what power of x solves the equation 2 to the x equals 10? All of a sudden it's not so clear. We know that x better be between 3 and 4 because 2 cubed is equal to 8 and 2 to the 4th is equal to 16, but actually getting an exact answer is a little bit tougher. This is where we define logarithms. How we define logarithms is the following. Log base b of y equals x is just the translation of b to the x is equal to y. This right here, the thing that I'm boxing, is a very important translation as it allows me to translate between logarithms and these very natural questions that we may ask. So therefore, if we're trying to solve this problem, which is in this form, we could write it in this way. So we just have to fill in the blanks. B, y, x. So, to translate it back to this form, we notice that b must be 2. So x is equal to log base 2, and then y is equal to 10. So log base 2 of 10. And this right here in red is a perfectly valid answer. So that's where these logarithms come from. They help us solve exponential equations. We're not going to be necessarily dealing so much with random bases. What we're going to be focused on is when the base b is actually equal to e, in which we'll have a special case of the logarithm. As I stated earlier, we're going to be focused when the base of the logarithm is e. So taking that box from the last slide, the one in blue, we have the following. Log base e of y is equal to x is actually just the translation of the statement e to the x equals y. Now, we don't like to do log base e because it's such a commonly used logarithm. We'd like to shorthand it if it's commonly used. So, instead of writing log base e, we're going to write natural log. These two dots right here kind of means defined as. So I'll be using natural log to implicate log base e. As a quick example of using this translation, what are the following? Natural log of 1. If we don't know, we can always go to this translation. If we don't know it in math, we like to call it x. Well, if we just translate this, we look for the base, we look for what y is, and we look for where x is, we can actually solve this out. This statement right here translates to e to the x, because our hidden base is e, equals 1. Now we have to ask ourselves, what power can we raise a number to give us 1? And the answer would be 0. It turns out that the log with any base of 1 will always be 0. So, next problem. Natural log of 1 over e. Well, since we don't know the answer, let's call it x. Now applying our translation, this translates the problem into our base, e, to the answer, x, is equal to 1 over e. This is a little bit less clear than the following one, or than the previous one. But one thing we can do is translate this guy one more step further. If we bring the e to the top, by making it a negative power, we have the following. E to the x equals e to the negative 1. Since the bases are the same, we could therefore conclude that x is equal to negative 1. This is a general feel of how logarithms work, and this translation really is the key to solving most things. Now before we get into deriving these natural logs, let's go over some important relationships. The very first one that we want to talk about is that the natural log and e to the x actually just undo each other. They are opposites. Therefore, I have that the natural log of e to the x is equal to x. And e to the natural log of x is actually equal to x as well. This follows from our translator. If I translated this statement back to that b to the x equals y form, I would get that you just land on x. And same with this guy over here, converting the other way. Go ahead and try it at home, it is worth doing. Now before we derive, these ones are really going to go a long way. We've noticed that doing algebra before deriving typically saves us from having to do a more complicated rule. So here's a little bit of definitional chasing that we can do to make the inside of the logarithm simpler. If I have multiplication on the inside, so the natural log of something times something, that actually can be rewritten as addition on the outside. So natural log of x times y is equal to the natural log of x plus the natural log of y. Similarly with division, if I have division on the inside, the natural log of x divided by y, that's just subtraction on the outside. The natural log of x minus the natural log of y. Last but not least, if we have the natural log of x to some power, or anything to some power for that matter, it doesn't have to be just x. I could rewrite that as multiplication on the outside, r times the natural log of x. Respectively, this will help us get out of a product rule, something times something, a quotient rule, something divided by something, and a chain rule, something trapped by a power. So these three in particular are going to be very worthwhile knowing. We'll go over a quick example about how to use these, and then we'll get on to deriving. Simplify the following logarithm. Natural log of x times the cube root of x squared plus 1. Well, the first thing that I noticed, and just like we do with deriving, think big picture first, is I have something times something. So I could rewrite that. Remember, multiplication on the inside is addition on the outside. So we could rewrite this as natural log of x plus the natural log of the cube root of x squared plus 1. And we're not done yet. This thing is simplified, but notice with that cube root, we could change that into a power. So we still have natural log of x, but allow me to rewrite that cube root as a 1/3 power. And it's important to notice, when I write it like this, the 1/3 is only affecting the inside of the logarithm. It's not affecting the outside of the logarithm itself. This allows me to go one step further. I can bring down that power. Power on the inside is multiplication on the outside, leading me to say, this guy right here simplifies to natural log of x plus, bring down the 1/3, 1/3 natural log of x squared plus 1. We cannot simplify that x squared anymore because there's a 1 attached to it on the inside. And addition on the inside does not simplify to anything. So this would be my final answer. Let's try another problem. The natural log of 3x times x plus 1 divided by 2x plus 1 squared. Go with the big picture rule first. We have a division going on. Division on the inside is subtraction on the outside. This simplifies into the natural log of 3x times x plus 1 minus the natural log of 2x plus 1 squared. And I like to draw these extra brackets to really inform me that, hey, that power is affecting the inside. From here, I can do two steps at one time. For instance, this multiplication right here, multiplication on the inside, leads to addition on the outside. So I could split this up into the natural log of 3x plus the natural log of x plus 1. Now over here, I have a power. Power on the inside is multiplication on the outside. So minus 2 natural log of 2x plus 1. These two are simplified down fully because there's an addition. I can't really split up that addition on the inside. I could go one more step right here because I have 3 times x and write this, since I have multiplication on the inside, as addition on the outside. Natural log of 3 plus natural log of x, and then the rest of the stuff that was trailed on. Natural log of x plus 1 minus 2 natural log of 2x plus 1. As we'll shortly see, being able to do something like this, if you follow me, we have a division, multiplication, and a power. That could be a quotient rule, product rule, and chain rule respectively. However, down here, we're going to actually avoid all of those. So doing this algebra will really help you out. Alright, now that we know about natural logs and kind of what they are and how they operate, let's talk about how to derive them. When given f of x equals the natural log of x, then f prime of x is just 1 over x. More generally, and this is probably a better rule to have memorized if you're going to memorize one, by the chain rule, applying the chain rule to something like this, if f of x is equal to the natural log of something with x on the inside, which I'll denote g of x. So natural log of something of x, then f prime of x is just the derivative of the inside divided by the original inside. So you can see that this applies to x. The derivative of x is just 1, and then the original inside was just x. Now yet again, this comes from the chain rule, but let me repeat it one more time. The natural log of something involving x, g of x, deriving that gives me the derivative of the inside divided by the original inside. Let's try a quick example. Derive the function f of x equals natural log of x squared plus 5x. If we derive this, f prime of x, that is just the derivative of the inside, 2x plus 5, divided by the original inside, x squared plus 5x. For those that are curious, and that is our final answer, by the way, for those that are curious why chain rule applies right here, think about a function, natural log of x, trapping another function, g of x. That will end up giving you 1 over g of x times g prime of x, but usually it's best just to remember derivative of the inside divided by the original inside. Let's get to a little bit more complicated examples now. Here are 3 quick examples to get us started off. First and simplest, let's consider y equals the natural log of 7x. Remember, if we're deriving this, the rule is the derivative of the inside divided by the original inside. That tells me that this becomes the derivative of the inside, 7, and let me go ahead and write y prime. The derivative of the inside is 7, divided by the original inside is 7x, which simplifies out to be 1 over x. Maybe a slight bit more complicated, what we could do is consider the natural log of x to the 8th power. Yet again, derivative of the inside divided by the original inside. The derivative of the inside is 8x to the 7th power. The original inside was x to the 8th. Now that leaves me with the answer, because I have 7x's up here and 8 down here, all 7 could cancel. We could just get 8 over x. Now allow me to pause real quick right here. We do have all of those rules from a little bit ago that we could apply to this. For instance, I have something to a power here. If you allow me, what I could have done is rewritten this as, bring the power down, power on the inside is multiplication on the outside, 8 times the natural log of x. I'll go and put this in parentheses. Well, if I derive this, that tells me, since 8's a constant, it stays copied down on the outside, but then the derivative of natural log of x is just 1 over x. So I get 8 times 1 over x, which actually just equals 8x. So these rules will make your derivative a little bit simpler. In this case, it doesn't necessarily matter because x to the 8th is a pretty simple derivative. However, let's now consider the following. g of x is equal to the natural log of the fifth root of 1 minus 2x. It will go a long way to simplify g of x first. For instance, I could write that fifth root as a 1/5 power. I could write this 1/5 power, power on the inside is multiplication on the outside, as 1/5 times the natural log of 1 minus 2x. But now I can derive this rather simply. The derivative of this, g prime of x, is just equal to, constant on the outside stays copied down, 1/5 times the derivative of the inside, -2, divided by the original inside, 1 minus 2x. Simplifying our answer, by just combining the fractions, we could get -2 over 5 minus 10x. If you did not think to simplify right here, when we do the derivative of the inside divided by the original inside, the derivative of the inside leaves me with a chain rule. Now this is doable, and you can do that, so if you're on the exam and freaking out and don't remember this thing, it's possible. However, it is a lot more work than just doing some algebra, so the algebra really will save your butt on this stuff. Let's talk two more derivatives. The whole theme of this slide will actually be that bigger rules still apply. So let's talk about the first one. Y equals a natural log of x, all raised to the fourth power. This one is very tempting to try to simplify with and to try to do a rule with, an algebra rule. However, powers have to be on the inside of the logarithm for me to bring it down to multiplication. In this case, the 4 is affecting everything. And by the way, on your homework, I will be very intentional about putting those parentheses, capturing the natural log of x. So therefore, I can't bring it down since it's on the outside, but I can apply a rule that we already know. When I derive this function, as I have something trapped by another function, trapped by a power, I have to use chain rule. Chain rule says the derivative of the outside, which is equal to 4 times the natural log of x cubed, times the derivative of the inside will give us our answer. The derivative of the inside, derivative of natural log of x, is just 1 over x. And that would be our answer. If you wanted to simplify it, we could write 4 natural log of x cubed, intentional about the parentheses, divided by x. And that would be about as simple as we can get. Power on the outside of logarithm cannot simplify, need chain rule. How about this one now? F of x equals natural log of x divided by x cubed. In this case, the division is on the outside of the logarithm, so I cannot make that subtraction. Therefore, I have to lean on a previous rule that we've learned. In this case, division leads to chain rule, or excuse me, quotient rule. So therefore, f prime of x is, by the quotient rule, low x cubed times d high. The derivative of natural log of x is 1 over x. So low d high minus high natural log of x times d low, 3x squared. All over the square of what's below. X cubed squared. In order to simplify this, we could notice the following. First, 1x will cancel right here, so this simplifies out to just an x squared. This guy doesn't really simplify much, so I could write it as 3x squared times the natural log of x. And then power to a power means you multiply, giving me an x to the 6th. If you wanted to go a step further, what you could notice is that 2 of these x's could cancel with the x's above. This leaves me with 1, since I canceled both x's, minus 3 times the natural log of x divided by x to the 4th as a final answer. If you really don't see how this step happens, just note that I could write this guy as x squared, factoring out the x squared up top, times 1 minus 3 natural log of x, all over x to the 6, from which I could cancel out 2 of the x's. Now let's dive into some implicit differentiation and finding the equation of tangent lines, since we have rules involving more derivatives now. Alright, now let's get some both implicit and equations of the tangent line in there now that we know how to derive the natural log of x and more complicated natural logs. First and foremost, find dy over dx implicitly given the equation natural log of x times y plus 5x equals 30. Now normally when we see x times y in an implicit problem, we think sneaky product rule. However, since we're dealing with natural logs, let's use those logarithm properties. Multiplication on the inside can be rewritten as addition on the outside. So therefore, simplifying but not deriving yet, this splits into natural log of x plus natural log of y plus 5x equals 30. Now let's derive implicitly. Derive everything if you directly derive a y, attach a dy dx. The derivative of natural log of x is just 1 over x. The derivative of natural log of y is just 1 over y, but I have to attach a dy over dx. The other way you could have seen this, by the way, is the derivative of natural log of something is the derivative of that something divided by the original. The derivative of y is just 1, but you attach dy over dx there, and then you divide it by the original, which was just y. Continuing on, derivative of 5x is just 5, and then don't forget to derive the 30, giving me 0. The process is now the same. Get all the dy dx's on one side, I'll keep them over here, so I get 1 over y times dy over dx, and kick everything else to the other side. Subtract over 5 and 1 over x. So we get negative 1 over x minus 5. Lastly, go ahead and get dy dx by itself. 2 ways you could do this, equivalent ways. You could divide by 1 over y on each side, but probably better yet, let's multiply each side by y. That'll cancel my y's on this side, leaving me with just dy over dx. And on this side, I'll just have negative 1 over x minus 5 all times y. Or probably better yet, if I distribute in, negative y over x minus 5y. And that is indeed my answer. Process stays the same from what we've learned with implicit. However, now we just have more derivatives that we can actually ask you. Continuing on, find an equation for the tangent line to the graph of f of x equals 3x squared times the natural log of x. I'm very intentional about saying times, at the point e comma 3e squared. Always a good day when we can get e involved. If we're ever finding the equation of the tangent line, recall that we're looking for a formula of a line, y equals mx plus b. Always start by getting the slope first. In order to get the slope, we need the derivative. F prime of x. Well, notice what f of x is. It's 3x squared times natural log of x. That means we have a product rule going on. So, in the spirit of product rule, that is first 3x squared times d second. The derivative of natural log of x is 1 over x. First d second plus second, natural log of x, times d first. The derivative of 3x squared is just 6x. Some simplification will help you here. For instance, one of the x's will cancel here, leaving me with a 3x, and then this side doesn't really simplify at all. 6x times natural log of x, which you don't really need the parentheses, I'm just putting them there. You could also factor out a 3x from each thing, leaving you with 3x times 1 plus 2 natural log of x. And I guess that's as simplified as we could get. Now, since I'm finding the equation of the tangent line, I go ahead and plug in the point I care about. Evaluate your derivative at your x that you care about, in this case, which is e. That will give me, by just plugging in directly, 3 times e, all times 1 plus 2 natural log of e. Now the natural log of e, one way we could try to figure out what that is, well, first off, if you have a calculator, just punch it in. We could actually do a little bit of this. Say you don't know what the natural log of e is. Let's call that something. Let's go ahead and call it y here. The only reason I'm using y is because we have x in the problem. Don't want to confuse us. By our translator, this thing would tell me the base to this power is equal to the inside of the logarithm. E to the y equals e. But that tells me, since there's a sneaky 1 right there, that y must be equal to 1. So we actually just discovered something. The natural log of e, the shortcut to that always just equals 1. Therefore, the reason we're doing this is because now I can just sub in a 1 right here. Equals 3e times 1 plus 2 times 1. Well, 2 plus 1, that better be 3. So ultimately, our slope is 9 times e. From here, we go to the our point-slope form to get the equation of the tangent line. Y minus y1. Our y is 3e squared, so y minus 3e squared equals m 9e times x minus x1. Our x1 is e in this case. If we go ahead and simplify this out, y minus 3e squared is equal to 9e times x minus 9. E times e is e squared. And then last but not least, adding over the 3e squared will give us an answer of y, after adding over, is equal to 9e times x minus 6e squared. I only include the parentheses right here because it makes it look a little bit like mx plus b. Now granted, those are weird slopes, but since e is just a glorified constant as we discussed in last video, that is a perfectly valid answer. So, in summary of this slide, we can still do the old things that we've done. We are just picking up new rules as we move along. Hey y'all, thanks for tuning in today with our exploration of logarithms and their derivatives. As a quick recap, first and foremost, logarithms come up and they help us solve exponential equations, such as 2 to the x equals 10 solve for x. That's where they arise from. The reason we like them so much is because they have very nice properties. As a quick summary, if you have multiplication on the inside, meaning the natural log of x times y, that leads to addition on the outside, the natural log of x plus the natural log of y. Similarly, division on the inside leads to subtraction on the outside, and powers on the inside are multiplication on the outside. These are very handy relationships which help you when deriving. However, all this was covered in your pre-calc class, therefore the most important lesson that we learned today was how to derive natural logs. If you have the natural log of something with x on the inside, indicated by g of x, then its derivative is just the derivative of the inside divided by the original inside. Remember to always try to use these algebra tools, these definitions, in order to simplify your derivative, because otherwise this g prime of x can get a little bit more complicated. With all that being said, go ahead and try your homework, give it a go, contact me with any questions you have. Other than that, have an excellent day.